The Altitude 3500 series access points typically have two radios, and each radio is capable of operating in 802.11a or 802.11bg mode. For the AP3510-IL SKU, only the 802.11bg radio is supported due to local regulatory restrictions. This family of access points can support up to 16 SSIDs, with up to 8 BSSIDs or MAC addresses. These units can also support up to 16 VLANs with 802.1q trunking. For wired VLAN connectivity, the Altitude 3500 series access points have two fast Ethernet connectors, a LAN port and a WAN port. On the AP3510, the LAN port is 802.3 AF-PoE power compliant. These units also have a console port to enable them to be managed through a serial connection. The AP3510 has a DB9 connector, and the AP3550 has an RJ45 connector. The Altitude 3500 series access points provide an onboard command line interface, or CLI, that is accessible to the network administrator through a telnet connection or through the serial port of the AP. The Altitude 3500 series access points support SNMP version 3, mesh networking, point-to-multipoint networks, point-to-point bridging, and a repeater mode. These access points each come with an integrated router, a DHCP server, a stateful firewall, built-in radius server, and IPsec VPN endpoint. The Altitude 3500 series access points also provide network address translation, or NAT functionality, and hotspot or guest access with URL redirection. The security features provided by the Altitude 3500 series access points include rogue AP detection, wireless intrusion prevention sensor capability, and 802.1x wired authentication. These units also support the PPPoE protocol. Firmware and configuration updates may be made using several different methodologies, such as through a VPN connection, or through a non-default VLAN, or even through a wireless mesh network. These access points have been certified by the Wi-Fi Alliance to support the wireless multimedia, or WMM extensions, including its WMM-PS or WMM Power Save features. The Altitude 3510 and 3550 and Motorola AP7131 APs employ an adaptive AP architecture. Adaptive APs may be managed over a wired or mesh infrastructure by a centralized wireless controller or as standalone devices. The adaptive AP architecture provides differentiation and choice by blending the management features and benefits of a thin AP architecture with the rich feature set of an independent or fat AP. Adaptive APs support centralized and distributed traffic forwarding. Client traffic may be tunneled through the network to the controller and then forwarded to the destination node, or the adaptive AP may forward the traffic directly to the destination node, bypassing the controller. Adaptive APs have several methods for discovering the wireless LAN controller and obtaining their configuration. This helps make the deployment of these access points truly plug and play. For extra security, the network administrator may enable an optional IPsec encrypted tunnel from the adaptive AP to the centralized controller. The adaptive AP can perform local encryption and decryption, relieving the wireless LAN controller of this CPU-intensive task. In the event of a controller or infrastructure failure, the adaptive AP has remote site survivability, or RSS, providing wireless LAN service resiliency. An adaptive AP will only adopt a controller at Layer 3. Adaptive APs support dynamic or manual AP load balancing. Adaptive APs can be configured to support unique country codes per AP. Layer 3 mobility is only supported with extended WLANs or SSIDs. A stateful firewall, Layer 2, Layer 3, and role-based, denial of service attack detection, and hotspot services on the controller can only be provided for extended WLANs. Encryption between the adaptive AP and the controller is only provided when IPsec VPN is enabled. Adaptive APs support independent WLANs and extended WLANs. While extended and independent WLANs have some features that are unique to each WLAN type, some of the characteristics are common to both. For example, both WLAN types may use centralized authentication, authorization, and accounting. The management of both WLAN types is centralized at the controller, with the exception of when the APs are connected to the controller via a VPN connection. Both WLAN types offload encryption and decryption of user traffic at the AP, and both WLAN types support rogue AP detection. Independent WLANs have the ability to provide local traffic forwarding at the AP. Independent WLANs may distribute the firewall function to the APs by performing Layer 3 stateful inspection firewall functions at the AP. Independent WLANs also provide IP filtering services on the AP. An example application for an independent WLAN could be a branch office deployment with a centralized controller. Another example application may be a real-time application that uses local forwarding to minimize any latency. Extended WLANs have the following features that are unique to this WLAN type. First, there is the centralized traffic forwarding. This type of traffic forwarding architecture enables the network administrator to have more control over the WLAN generated traffic that goes onto the LAN. The extended WLAN provides a centralized L2, L3 role-based firewall. Other features include denial of service or DOS attack detection, ARP and DHCP spoofing services, centralized hotspot services, and locationing. Applications requiring centralized firewall services or a centralized hotspot guest access application are good examples of applications that would benefit from the features provided by an extended WLAN.